Okay, well, let's start Math 115, fall semester, probability and statistics. So we're going to start off with the very foundational ideas, and, and it has to do with, we all know the statistics has to do with data, and we have to talk about what data is, and we're going to find out that data is going to be a kind of an amorphous collection of ones and zeros that have no intrinsic meaning. I'll show you some data. Uh, you won't be able to deduce anything from this data to start with. So one of the first goals is to transform data into information. And we'll see how that's done. Once we have information, then we can begin to organize the data into formats that would begin to understand what the data is trying to tell us. And once we have a collection of information in a way that becomes useful to us and meaningful to us, it is transformed into knowledge. That is to say, we now know something about this particular data set that we didn't know before. And ultimately, the purpose of all of this is to transform knowledge into wisdom. And the goal of wisdom is just to make good, wise decisions. So let's start off with this concept of data. So as I was saying, data is just an unorganized collection of facts. I'm going to show you some data in a moment. Usually data takes the form of numbers and on its own has no meaning. So here's an example of some data. There you see it, and the data is actually organized vertically in this case. So we're looking down these columns, and that comes around. We'll look down this column. So we're seeing 1, 0, 1, 0, 0 as we go down the column. And you have to wonder, does this mean anything to anybody? Does it have any value? Can we deduce anything from this? Does it represent anything? And what are we supposed to do with this? So in order to understand what to do with it, you need to know a clue. You have to have a clue as to what this is about. And I'm going to give you that clue. That first column, 10100, I've transformed into something that lists those first 5 numbers in a way that you might be able to deduce some information. So that first one, right up here, represents something that went on in 1903 having to do with something called AL. And the second number in the data set looks like it has something to do with something that happened in the year 1905, and it has something to do with NL. Now, if you're at all, if anyone has ever taken you to a baseball game, you probably have figured out, oh, that's the American League, and NL is the National League, and it's something that happens every year, except it didn't happen in 1904 and didn't happen recently, a few decades ago, but every other year since then it happened. And it involved the American League and the National League. And so you're probably thinking, you know what this is? This is a record of who won the World Series in each year since the World Series started. And we've encoded the American League, AL, as the number 1 in our data set. And we've encoded the National League as the number 0 in our data set. And so if you look through this data, you will see that every one of these numbers represents a year that the World Series was played and who the winner was, right on down to the last winner. What's that? Right under the last winner, well, that's the next to the last winner, was won by the American League this was in 2013. Okay, so we can see that data can become something we call information. Data that was meaningless acquires meaning as it becomes information. Data is boring. You can look at data all day long and not be interested, but even this tiny little bit of information that we see here kind of interests us. Data doesn't suggest what to do with it. if we look at this series of ones and zeros, it doesn't really offer any suggestion as to what am I supposed to do with that. But when we look at information, it practically begs to summarize itself. For example, as we look at this sequence of ones and zeros, we can ask ourselves all kinds of questions. We can find out which league won more World Series. What fraction of the World Series was won by the American League, by the National League? Here's something interesting. What was the longest winning streak? What do you suppose that is? Well, we can now find out. We can find out who won the first World Series. Well, we already know that. That was the American League. And most recent World Series was won by the National League. What's the average number of times each decade each league has won the World Series? That'd be an interesting question to ask. And what's the probability of the American League winning the World Series? And we have to talk about, there'll be a whole section of the course having to do with this very, very slippery slope word, probability. Oh, and we can look at patterns in time. Has the winning or losing of the World Series changed over time? So all kinds of questions that information leads us to ask. All right. So the goal of statistics is, the first goal is we need to extract meaning from data so that we have some information to work with. And we're going to be talking the first part of the course about descriptive statistics. And that is to describe a data set so that information can be extracted. Okay, the next goal of statistics is we need to get knowledge out of that information. So we're given a small bit of data. What can we say about larger volumes of data? Can we gain knowledge regarding how one variable is related to another variable? Do we see any correlation? Is it possible to conclude causation? What can we conclude about cause and effect? So when we do that, we're in the realm of inferential statistics. And we're going to talk about inferential statistics in the latter part of the course. So finally, how can this inferential statistics inform our decisions so that we can make wise decisions and good decisions? How can we manage our lives and our resources more wisely? And that's really the highest goal for statistics. It may seem very mathematical, but ultimately it guides decisions we make in our lives and establishes policies that we make for societies. So it has a very high calling. So there is what I call the information ladder, or the statistics ladder. And we start out with sort of amorphous data that either we're given or that we can collect. And that goes up the chain to information. And that is the job of descriptive statistics. So we'll let the descriptive statistics take us from data to information. Once we have the statistics described in the form of information, the job of inferential statistics is to develop a knowledge out of that, to be able to make broad-ranging, wide-ranging statements about much larger populations than the small piece of data that we gathered. And ultimately, and the statistics can't help us here, can we become wise? And I would say that statistics sort of stops at that point, and the rest is up to you. All right. So another way to look at this picture is this way. We start here at the bottom with this population. By population, it doesn't necessarily mean a human population, although very often it does, but it can be a population of all kinds of numbers. Say the number of ships that were built by the Kaiser Company in World War II, or it could be the number of pizzas that are sold by Round Table in any given month, or something like that, where there's what we call the universe of data, where it's all the data that actually, it's so much data we can't really know it all. Suppose, for example, this population is this big blue disk were our country, and each of those little dots were people. And we wanted to know, say, the average number of cups of coffee that people drank during the day. Well, we would have to go out to 300 million people and round them up and ask them a question and record it and so forth, and that's just not practical. So the population is full of really unknowns. We can't know the real parameters of the population. So what we can do is we can sample the population. So we take just a very small number of those dots, and the idea is to take them at random and pull them up into a little tiny set, and that's called the sample. So those are the two important words here: is population, which is all the data there is for a particular topic, and then there's sample. Now sometimes a population is small enough that we can gather all the data in the universe of that data. For example, all the students of this class. We could find out, say, the age of every member of the population, or we could find out the height of every member of the population, something along those lines. There wouldn't be any other population to know about, and there we could determine very precise results. But if the population were, say, all the students that went to the College of Marin, there's 10,000 enrolled students. We can't really go out and round those people up and have them take a survey and gather all that. Even if we could, it might be too expensive or take too long. So instead what we do, we identify at random some of those students, and we then put that collection together to form a sample. So a sample is a subset of a population. The population is the whole enchilada. The sample is a subset. So the idea of drawing out this data, and I have these backwards, but we can describe everything there is to know about the sample because it's small enough. And with the knowledge of the sample, we can then use inferential statistics to come back and tell us, to inform us what's going on in the greater population. So keep in mind the difference between sample and population, and the difference between descriptive and inferential statistics. So here's another overview of how this works. So here we have, in this representation, we're looking at a population that is unobserved. We can't observe it usually. As I say, it is possible that we could pick a very small population and know everything about it, but in general, populations of data are too much to go out and measure. So we say that the population is unobserved. But we do have random sampling, and that's what that arrow means, is to withdraw or to draw out of that population a small number that we can afford to gather, but large enough so that it has meaning. For example, if you wanted to know the height of American men, it really wouldn't do too much good to just pick one American man and say, well, that's the height of all the American men. You want a sample size that's large enough to be able to do you some good. So the sample is data that is observed, not unobserved, but observed data. You know everything about the sample. So from the sample, we use descriptive statistics to measure quantities that are called statistics. So we're using the word statistics here in two different ways. One is, statistics is this art and science and this mathematical topic that we're going to be learning over the next 17 weeks. That's statistics. But statistic, and the plural of it, statistics, refer to quantities about the sample. Quantities about the sample. For example, you could measure the mean of the sample. If we were interested in the heights of American males, we could say randomly pick, oh, I don't know, maybe 200 American males, and we could then calculate the mean or the average of that number, and that would be a statistic of the sample. So once we've done our descriptive statistics and we have this collection of statistics about the sample, we then use inferential statistics going in this direction to compute what are called parameters. And for every statistic, there's a parameter. So we talked about one statistic being the mean. I'm going to write this as x bar. Let's say that's the mean of the quantity that we've measured. And we're going to use that to calculate the mean of the population. And this is the Greek letter mu. And that stands for the mean. And that's a parameter of the population. So we gain from this, we come right back up to the population. What did we gain? We gained knowledge about the population, but there will be uncertainty. There will be uncertainty, and that is something we can't get away from in statistics. There's kind of the overview of how that works.